Then to have a graph visualization system that's based on physics, we need a physics engine. And so I've defined a very simple 2D physics engine in this class Bolt. And this interface is the is the contract between this physics engine and its clients. So the client feeds this Bolt class with objects of this shape. As we can see, we have position, we have velocity, we have mass, we have friction, we have this force by function that tells our physics engine how much force is exerted by this object from other objects.
Are you examining every object in your graph?
Yes.
It would be interesting. So some problems may lead to huge graphs. It would be interesting to use a simple metric to.
I'm doing stuff to cut down on the computation.
Okay. Good.
One of them, I'll show you one example.
Okay, good.
But in the things that I've tried, it's been working fine.
What's the max number of nodes you used?
Maybe like 100 something.
Oh, really? That many? Oh, okay, good.
Okay, so our physics.
Do you get, so here you are with TypeScript in VS Code. Do you get IntelliSense from
Yes, I get very nice information. I'll show that to you. So this is my physics engine, my Volt class. As I said, I have an array of these physics objects that the client just fills. And the main function of this Volt class is this tick function. Whenever the client calls this tick function, the physics engine does a little bit of computation, moves like the state of the world forward a little bit. I can show you how that is done. So here I calculate the forces using that force by function that I showed you, and then I iterate through the objects and update their positions and velocities. So here, for example, here is where I update the velocity, and this is the simple physics behind it. So delta V is equal to F times delta T over M, and that is exactly what I'm doing here. I'm saying change the velocity by the force times the delta T divided by mass. And here I'm doing the same thing for position. Delta X is equal to V times delta T, so update the position by velocity times, again, time delta, which is the same.
So you're using an explicit integration scheme, basically. Yeah. Right.
To me, it's like simulation. To me, it's simulation.
Yeah, but I mean, that's what. So the explicit integration schemes, if you integrate a system of linear differential equations, they're doing a simulation.
I think what you're using is.
But I'm running this in real time.
I think what you're using is basically
wait a minute, let me finish my question, okay? You're running it in tick time. So the point I was getting to is explicit integration schemes can go unstable if the tick time gets bigger than some fraction of the smallest time constant system, which is determined by
Yeah, that's true. But I'm not doing simulation for, I don't know.
Just an
critical-
observation, I was wondering if you
critical
ran
things.
into that problem or anything. You know, once you start getting a lot of nodes, you probably have, you know, quite a big span of eigenvalues in the, you know, in your, representing your system, and so you might be interesting. See whether you got into that. There's things you can do.
I'll
with it.
show you what it looks like.
So you're using is essentially a half Euler Newtonian
Yes.
method. It doesn't preserve frequency, but it might get unstable if there is oscillation. So have you run into the problems? Like the graph will get oscillate more and more?
And
That was the question I was asking.
Yeah.
so I have friction.
No, but it still might get
When I have friction, it
Friction
it
does
erodes
help.
the energy, so
But
it
Friction
finally
dampens
stabilizes.
the natural system, but the point is that you're transforming it into a discrete system, and that explicit integration rule, Euler's or, you know, whatever, can make a stable system go unstable. And the rule is if the time step is significantly bigger than the smallest time constant in the system, it'll go unstable. And what that relative size depends on the algorithm you use. Euler is one, you know, Runge-Kutta is another, you know. But didn't expect you to solve that or even worried about it much. That was just a.
I mean, we can play with it. I have, like I said, I have friction in the system, so it always.
Friction makes the
Stabilizes.
real system dampen,
Yeah.
but it doesn't necessarily make this artificial approximation dampen.
Here's another way
What do you mean?
to say this. If you're using a different simulation method, it might not retain frequency, but they retain energy. In which case, it will dampen itself. It doesn't. You don't need to introduce friction. It will still oscillate as normal.
I think I always
So
need friction.
we're really just trying to ask: is that part of the equation, or have you ever considered that?
This is
It's fine. Yeah,
but,
it's very fine.
But I think I always need friction.
No,
Because
that
if there is,
it's
you
part
know,
of
if,
the
you know,
model.
if there are
It's not
forces
that.
in the system and they
You
cause,
do.
they,
You're right.
there's
You're right.
energy and the energy turns into, you know,
You're right, you do, but
kinetic
that's.
energy and things move forever.
That's
If
part of
there
the
is friction.
physics.
That's necessary but not sufficient for stability of your simulated system. That's necessary but not sufficient for stability. I can tell you from long experience doing scientific programming that is necessary but not sufficient.
What is necessary?
So basically, you have to maintain the friction.
You're transforming the system from a continuous time set of a couple differential equations into a discrete system, and that transformation can make it go unstable. You can look at the way the poles move, you know, now in a discrete system, it's the unit circle that matters, the stability boundary, and you can see those poles map out of the unit circle as you take bigger and bigger time steps. It does happen, even if you have model friction. But you know, we're pulling you off the topic, and so let's show this.
I'm actually interested in this.
We can
But,
talk about it later.
you know, but I thought if there's like a little bit of friction, no
That's-
matter what happens, it will eventually
That's true if
stabilize.
you have an exact representation, but you don't. You can look at, there's a famous implicit integration. Implicit integration tends to be always stable, independent of the step size. There's a famous integration algorithm called GEAR, by a guy by the name of GEAR. And if you look that up in Wikipedia, GEAR's integration scheme, they'll talk about all that.
Okay, I'll look
If you
it
can't
up.
find it, send me an email, I'll give you some.
Look it up, thanks. So,
This is only of interest to the three of us, so I'm trying.
so so this was my physics, simple physics engine. Now let's move on to the next probe. So my project is about graph visualization. So I have a graph visualizer class. This graph viz class, it takes an HTML canvas and a graph and and visualizes it. And it uses that physics engine that I showed you in the last probe. So as I mentioned in my first presentation, I'm using Easer.js, and since I'm using TypeScript, I just installed the typing definitions for Easer.js, and that makes life a lot easier. I can just demo that for you.
I assume that TypeScript can be coexist with native JavaScript, okay? Is that true or false?
That's true. But what that typing definition information does is it just at development time provides typing information for the same JavaScript code. I do not have to use it, but using it makes life easier. So let's see our graph viz class. This is the graph viz class, and as I mentioned, it takes a canvas, a graph, and a bunch of other parameters, and visualizes the graph. And like I said, I'm using Easer.js. Here's a small example of using Easer.js. So here I am creating an Easer.js object, a container, and add to it a circle to represent the node, and a caption to label the node. And but working, this is what the typing info provides. So if I dot here, this is an Easer.js object. I get all the methods and properties available on it. So for example, I see a shadow property here. I can try to figure out what that is all about. So this is supposed to be of type create.js.shadow. So I say new create.js shadow, and the shadow takes a color. Let's give it a color, gray, for example. Bunch of offsets. So let's give it offsets, and
Those are pixels.
I would imagine so, yeah. And a blur, which is a number. So since I don't know anything, I'm going to give it 1.
The alpha.
I don't know. But we can try and see what happens. So I've changed my code. Let's see. Let's see. So we see the shadows, right? So but it doesn't look so good. Here, change the value. Maybe if I change this. The value it would look better. It looks better now. So that was a small demo of using TypeScript.
Does TypeScript get compiled or translated into native JavaScript before it runs?
So what I have here is I'm running this. I'm running this TypeScript compiler in watch mode, and if you can see, I know it's small. And what it does is it just sits there, watches for any changes to TypeScript files, and whenever it detects any change, it goes and updates the corresponding JavaScript file. So, for example, this is my TypeScript file for GraphViz, and this is the corresponding JavaScript file. And I can target, different versions of JavaScript. I'm targeting ES6, so I'm compiling it to a class. If I target ES5, it does, all the prototyping stuff and constructor functions and so on.
Might be a nice way to explore native.
Yeah. Okay, so that is that. And but there's one more thing that I wanted to show. Well, I as you saw, the nodes were randomly placed at first. Just wanted to make that point. And the forces. So this GraphViz class is also responsible for defining the forces between nodes. And this is how it is defined. So I'm saying if the two nodes are connected, the force is like a constant times the displacement from the natural size of the node, of the edge. So if they are too far apart, they attract. If they are too close, they repel. And if two nodes are not connected, the force between them is repulsive, and it is, like I said, inversely proportional to the square of the distance. There was one point I wanted. So here's an example of me cutting corners. So I'm saying if the objects are not too far apart, do the computation, otherwise just return 0. And that GraphViz class has a few knobs that can be tweaked at runtime. I'll show you that in a bit. So this is my final probe. And the final probe is basically just putting things together. So in my main TS file, first of all, I have a bunch of test graphs that I've defined here. And it doesn't do much. It just, takes a graph and uses that GraphViz class to visualize the graph. And what I'm doing is I'm ticking, calling the tick function on the word on my physics engine 60 times per second. So that was a smooth animation. And I can wait. So if I click on any of them, this is like a molecule cyclohexanol, and after a few seconds settles on something that we can make sense of.
Can you adjust the tick interval? Is that a parameter for your visualization?
Not right now. Okay. I have like other parameters. Like
Yeah.
like we see friction, the edge length, the repulsion, and so on. So this is one example. I can show you other examples too. So this is another example with a lot more nodes. Takes a bit longer to stabilize, but but it does. And the one thing we can do is we can increase the friction, and that makes things stabilize more quickly. But it might not be as ideal.
You could increase the friction, and then as you got closer to steady state, decrease it a little bit.
Right now, it is
Yeah. There's lots of things you could try. I'm with you. And it does a really nice job. I've always liked these force-driven layouts because I think they do a really great job. The one thing that would be interesting to try would be to represent your mouse and have the mouse have a repulsive force. So you got a cluster that you want to pull apart a little bit, so you pull your mouse up into the cluster and the cluster push apart.
I'll show you something on that in a little bit. But I just wanted to show how tweaking these knobs work. So this is a complete graph, and everything is close to each other. So you can just increase the edge length, and they get further apart. And on your point on moving things, this is what I can do. This I can just grab the nodes and move them around. Gotcha.
Somebody did a project, not exactly like this, but this version, this project's a couple of years, 2 or 3 years ago. And what they did was they calculated the center of mass of all those points, or center of gravity, or whatever, of all the points, centroid of all the points. Then they kept moving. So they put forces on to move the centroid, so it was always in the center of the screen.
Yeah, that's an idea. So this is one I wanted to show this because this is a tree with a hierarchy. So I thought it would be nice to show a tree with a hierarchy as a tree with a hierarchy, but where the root of the tree is at the top. So I thought to do that, I only need to pin one of the nodes. So here, this node is pinned; it doesn't move, and add gravity to the scene. So everything hangs from that piece node. That is it. So I've put my code here. You can give it a try if you want. And this is my project timeline. So I was supposed to do the graph drawing and so on, which I've done. And I'm done with the physics simulation as well. I can move the nodes around with my mouse. That is done too. One thing that I'm adding to my timeline is loading these graphs from files and saving them to files. This is something that I didn't have before. Something that I'm thinking of not doing is wrapping this in an Electron shell because I don't think it adds a lot of value here. And one thing that Professor suggested was having the ability to annotate the graphs, like click on a node and write a description for it and something. So I'm trying to do that by the presentation. And that's it.
Any questions for Irash? I liked your presentation. I thought it was really nice. You scrolled through the code too quickly. I saw the blur of code going up and down, you know.
Okay.
But aside from that, it looks very well structured, very well put together, very professionally put together, and you know, your presentation of the probes is right on. Just, you know, that's what I want in the class. You know, here's what I tried, here's why I did it, here's how it worked out. Good job.
Question?
Okay, who's next? Lucian, yeah, okay, good. Yep, Lucian. Is that the right way to pronounce your name, Ruchi?
Yes, quite a bit.
That translates it, not really, but I know it's the best you can do. So for you guys who came in late, I've marked on the board, I'm trying to grade your project ones this weekend, so please upload them. We still need to schedule a time for you.
This weekend.
One. Yeah. Send me an email about it on Friday, so Saturday I'll think about it and we'll. Oh, I didn't schedule it already, but I told you I would schedule it for this week.
Yeah, this week.
It ain't gonna be this week. Send me an email, but we'll do it the next week for sure. Yeah.
Should
I want to do you and Arpit at the same time, just for
Maybe next
my
week.
own
Okay.
survival. Okay.
Okay.
Yeah.
So,
Next week sometime.
Yes,
That'll work for you,
yes,
okay,
yes.
right?
yeah, that
Okay.
works.
Just send an email on Friday or
I would prefer, that way I'll see it at the top of my email on Saturday morning. Saturday morning is the first time I'm gonna really get a chance to look at it. Oh, good. Also. Okay. Yeah, I can, I don't know. Yeah.
This one first. And that is that's an awkward
Okay.
situation.
All right. Is that gonna work though, the way it's set up now?
Yeah, I think it should be. Let me just.
Okay, yep.
Right. Um, Good afternoon. This is our second project for our embedded photo booth. Let's first review of our object summary. So what we plan to do is we plan to develop a embedded photo booth using the Raspberry Pi, and they can take a photo using the Raspberry Pi, and the photo can be uploaded to the cloud server, and these photos can be processed with artificial backgrounds, which means backgrounds of photo creates a sort of different picture, and these photos stored in the server can be downloaded via a browser. So here's some review of the technology we mentioned in the first class. For on the Raspberry Pi side, we plan to implement everything in Python. We did plan to do something in OpenCV and C++, but based on the testing, there is so much difference in performance. And for simplicity, we Python. And for the cloud server,
So there wasn't much difference in performance because the C++ stuff was a tiny part of all of what you're doing, is that why?
yeah, we just called function inside OpenCV, and because because we're writing the GUI in Python, and it has to create
Yeah.
a separate thread to process all the image, and if using C++, it might be really hard to trick around.
Yeah,
So,
that was, you were replacing a small part of your whole,
yeah, it's communicating two different
Yeah.
threads in two different languages, so that's why we abandoned that part. And for the cloud server, we implement using Node.js and MongoDB to store the key to retrieve the file, and for the web browser, we use HTML.
are all the Python modules you're using widely supported? I mean, they're under active development and stuff.
What do you mean, Professor?
Well, it's not uncommon for open source projects to be popular for a while, and then they die off in popularity, and there's no more activity, and they become more abundant.
We only use Wixie, Python, and OpenCV
Oh,
in this
okay.
project, so I think that they're pretty still very much alive these days.
Yeah.
And here's an overview for the three major parts. Raspberry Pi, you got the GUI for the user interface. Inside, we got a photo processor with Python, OpenCV, and the photo upload. And the cloud server stores all the files. So we wrote in the Node.js, and then there's a browser client. So that's how it works. So our first program example is for the OpenCV Python. So the first thing we try to do is how can we achieve the background of the image, and another thing is we want to add the auto movement mode, which means when the user has a movement, the photo booth automatically takes a photo of that moment. So in order doing so, we did a lot of tricking tests in OpenCV. So let me. So the first example, the code we run is we test several different CV processing functions to see which one offers the most real time performance we need. And the first one we test is so basically. This one using the Pi camera module offered by Raspberry Pi. This uses the built-in camera of the Raspberry Pi, and this raw capture just creates a series of image. And for line 15.5, we convert this image to a gray color image, and then we start our processing. So the first method we try is just do a absolute difference between the background and the current frame. So we call it the frame difference. It's right in line 28. And then we convert this grayscale different image to a black and white image. That should be the mask if it's ideally for ideal performance. And another thing we try is there is a background subtractor offered by OpenCV. It's a very complete function. We also tried this one. And the other thing we try is whether to smooth the picture. Because if this one is steady enough, it should offer, like the background should be the same every frame, but actually it's quite different. So let's run this and see the difference. So that's the image. On the right left upper corner is the original image, and below is the grayscale. And what we found is actually this one, which is the background subtractor. It doesn't perform as we assume. It doesn't very precise. So we opt for a very simple method, which is this one. It just do an absolute difference. For the movement, we're just doing the absolute difference between the frames. So now we are running in 480p at I think 15 FPS, and we did try 30, but it still performed like 15. So we didn't go any further with that. And this is our first test. So we decided to go with just the absolute difference. So basically, for all of the frames, we convert them to grayscale. Then we do an absolute difference between the background and between the current frame and the previous frame to get the movement. And we convert those two differences into a binary format. So that's the first processing test we. And the second test, we want to see whether we can change the background. So basically, after we grab the mask from the background, the current frame, like we showed in the previous test, the difference image in the binary format is our mask for the foreground of the picture user. So basically, we apply this with the mask, which just like cuts off the user from the photo. And we use an invert mask and applied it with the background picture, combined together. So so that's what we test for the background using. How it looks like. The forest. This is where we are now. So it's quite light here, so I might need to pick around the press a little bit for a better performance. But as you can see, out frame, my hand seems in the forest. Pick around for light, and you should use it in a very dark room. So that's the second one we test to replace the background based on the mask and the like the other processing we could test for. This is how we get from our test. We test in a very dark environment. We didn't use chroma key at the moment, and here is I think the result is quite acceptable. We get the yellow toy inside the voice. And the second probing test we did is about how we can implement the target GUI using Python. So this is what we want to achieve based on our first presentation. We want to have a display panel display the current frame the user is going to have, and we have a capture button, basically capture picture. An auto button is toggling between the auto mode and manual mode, and the set button sending everything to the top server. And we have three different backgrounds. One is the way we implement this one is we have a capture, we have a real background, but we offer two imaginary background. One is forest, and the other one's in the space. And we have a chat box to where is capture on movement. We haven't tested the sent so far, so. So the main window is how we implement the GUI with Python. Basically, the initialization part we define a camera, and we only capture the background here. So before everything starts, we capture background, and then we have several like the image CV file we have for processing inside. We initialize them, and we create a true BMP file inside the GUI to represent the current frame and the latest photo taken. And we start everything. So the only thing I mentioned before is we need a process like keep running, keep taking the picture, grab a picture from the Pi camera. So what I did is I create another event. We call it the CV stream event up here. So this event is so I create another thread here, and this thread is consecutively grabbing a frame from the Pi camera, and after a successfully grab a frame from the camera, it sends this this event back to the parent frame, so that the parent frame knows it has available frame for the processing. So so the rest is just like all the GUI application we wrote in the language, and let's test this one. Take some time. So now it's running the image on the left is like what camera is reading now. We are also running this in 480p at 10 fps. So let's say we capture. So we just capture one image and it's showing on the right side. And we can toggle between different backgrounds. Let's say we don't see our hand in the forest. And we can get in the space background. And we can get this chat box is actually the auto movement. There's movement. Based on movement, and the movement detection is done through. So once if there's a countdown zero, means there are too many black pixels. There are two less black pixels between the difference of the binary image of two in this movement. So that's how the code is. And there is a number tracking how many pictures you take to a different file name. So this is a quite bit of work of our GUI application. We haven't added the send, and we haven't add like a different folder for different users because we do everything in the same file. So next, my partner Jing will talk about the cloud server.
Could you talk a little louder?
Oh, okay, sure. So our goal for the cloud photo server is we want this server to upload and download files and also manage data. So we want our server able to file upload and also save the uploaded file to storage, and further we'll have able to insert the photo ID and file path as the key value pair to the DB database, and also at last able to handle requests from the client browser for the file download. Sorry. So this is our index JS. I think it's a little small, hard to see, but we first have our needed model all defined here, and we have our MongoDB database. I use Mongoose here to connect to the default port number and give the database name as MyDB. And I also define the file schema as will contain two key value pair with ID and string saved with, and also the path, and also the string. And when the actually the upload request will done by the Raspberry Pi, but here I just mark the upload request as here I can get the upload if go to the upload, I will send a HTML file which I can input the file I want to upload and also the photo ID and file name. My server is begin to here at the port 8000. Our web server IP address and go to the upload. So it will have this HTML form, and there I can choose how to update. But it is one zip as example, and I also will give a photo ID which will provide to user to retrieve their photo. And this is success to upload to the database where here has the hint. And for this upload function, I define here, I have motor to help me down the upload. As I can see here, I have a storage and which define the destination and also the file name. The destination is simple, just the same under the same root of the index dot. And also, after the upload, I set up a callback function, which will extract all the zip file to a folder that contains JPG, because we finally want to display all the JPG photo to the browser. So it's easier to, and then I just create a new schema which I defined about to insert the ID, which is the photo ID, and just input, and also the path, which give as the upload files and also the file name. And after this callback function, I just save the schema to the database, and if it is succeed, I will have the success. So here we can see save status success, so we can know that the file is successful upload to. And then so for results, I can see that we are able to handle the upload request, also save the zip file to storage and extract, also to save the photo ID, which will provide to user and file path to. And this below picture is just a simple test result with what I done in home. And next is our web browser client. We want to have our web browser able to retrieve and display the photos after user input their photo ID, and also able to download the selected photos. And for handle this function, I define a get photo, which I can or IP address, and it will just come out this simple form to input the yes and press get photo. And because finally we want to display the image, and I'm still working on it, so it just becomes one, but actually it will be redirected to another HTML and to display photo. And but now we are able to download the file to the downloads, which we save to the database. And
Okay.
yeah, sorry, it's too.
It is 4:27.
This works, so we will finally for the results, we are able to retrieve the file by photo ID, and for further function, we need to support image display and also the select button. So summary of the probes, what we can say that we have done most part of the implementation, and for me, I will finish the client browser image and also provide detailed HTML, CSS file for the browser.
I would be interested when you do the final presentation, if we change the lighting a little bit here?
We already bought a chroma key from Amazon, and it is on its way, so we will test and.
Okay, because I think I think while you did a credible job, the lighting is awful.
Yeah,
You have that
quite
recessed lighting.
I think the OpenCV part wasn't quite different. It's just tweaking around different functions and the parameters. But the Bixby Python really gave me a hard time because I initially thought it's like what we did in OD, we use Q to communicate with the GUI, but actually it's not. So that part, I think the event-based part is it gave me a hard time. For this part, the OpenSea part, I think the Lightning. The funny thing we found is we wrote two versions actually. The other version we already commented is like we define all the background as none when initialized, and when we're in the cycle taking pictures, when we found the background is not defined, we assign this frame to the background. But compared to this, with the we take the picture assigned to the background during the initialization, the result is different. I don't know why, but they have very huge difference in performance. If we do not initialize a background, we just assign a random frame, the first frame from the camera during the capture process, the result is very bad. Seems like the photo looks very different. We don't know why. We tried to figure it out, but we didn't find an answer to that part. But yeah, why it's amazing to the lightning here? Probably because they did a very good job in the library.
Doing image processing, I've done a little bit of it myself, and it's so hard to debug.
Yeah.
Because you get stuff that you can't trace and you don't know why you got it. Good. Any questions of these guys? Thank you, guys. So on Thursday, we're gonna hear from Ten Ming and Zidong. Right? No, I'm sorry. Ten Ming, are you here? Ten Ming is not here. So Zidong, yeah, you're Yaodong. Zidong, yeah. Sorry, I get the names mixed up. So, and he's not here either. That's interesting. Well, and then I have the Wei Jun Kai is going to present on Thursday too. Wei Jun, not here. Nobody presenting on Thursday is here. I hope that's not a bad sign. All righty, so get me your project ones. If I grade them this weekend, that would be great. And I owe you feedback on your presentation so far, and I'm going to be working on them this weekend. Hopefully I'll get both project ones graded and your feedback done, and we'll get that on Tuesday. Alrighty, guys, and we're scheduled for the final presentations on the 3rd and 4th of May. It should be a Saturday and a Sunday.
5th and 6th.
5th and 6th. Oh, this must be an old version. It's the Saturday and Sunday, right? That's the 5th and 6th. So that's when we're. I'm assuming nobody has any problems with that. I don't want to get an email message on Friday that you can't present on Saturday or Sunday. Your obligation, I would like For those who are presenting on Saturday, I'd like you to be here all day long so that everybody has an audience. But you don't need to come on Sunday. For those of you who are presenting on Sunday, you don't need to come on Saturday, but I'd like to have you here all day Sunday so that everybody has an audience. All righty, see you all next week. Some people have that, my intent was that, obviously some of the presentations are pretty close to the final. My intent was that he didn't tell us everything about the program. What you need to do is what I want you to do is focus on making more readable slides, bigger fonts, say less.
And if but not in the long run, because you have to adjust the
Yeah, for a little, I can't stay too long, but we can definitely do it now.
but if you use a proper model, that won't be. I think the half euro doesn't
Okay.
so the normal Newtonian method, very
Yeah, I think this week I have to call you.
when there is an oscillation, even in
Yeah, okay. Is the repository is supplying the version
you
numbers?
will gradually
Yes.
As they're being stored, yeah.
Yeah, the server, at the server side, I have an.
You've seen that? Yeah, definitely you will see that.
Logic.
That's
Like
majorly the
you
problem.
gave
The version number
Yeah.
for,
file.
things about
Then I'm doing
It should be stable if you're using a correct
file with
map,
all the
but the
versions.
simulation model doesn't.
Going into the file and
You
all
have
the
to use a
versions.
different.
Then I'm doing like
But you could also introduce a larger friction zone,
the server.
change the.
And
That's
But I think with
lot of
friction,
these.
Yeah, that sounds fun.
Yeah, but the simulation model.
So how
introduce
busy are you now?
a-
Is the
like-
busyness done for a while?
Method in a simulation way.
Or do you have a bunch more interviewing to do?
No, you introduce energy, so it's the same way. So you can't fix that from the.
Well, we don't have much more than one.
At least not on the long term.
whatever energy is out of the friction just takes to the.
Yeah, I get what you're saying. It works. It doesn't work on the long run. It's not on the interest resolution.
Helper code.
Mhm.
I thought of doing that.
The simulation model.
Doing all this
Yeah.
Yeah.
And you have a model
luxury.
not under control.
Yeah, so what's going on?
If you identify things that the energy goes down. Even if
Presentation was a little light.
Also,
You're in
Yeah, that day I was not done with
you're
my
in B plus territory, and so if you want to do better than that,
It
you
works,
need to
but
get a
the thing
little
is-
more. You need to get as much functionality as you can.
If the
End of the
flaw,
project. I'm not saying throw every bell and whistle in, but what you want to do is get as much together and work well as you
math is
can.
correct.
And
Model is-
it's fine.
So you can't fix this.
The important thing is the final presentation, not so much the,
That works.
the
That works.
makeup presentation you're gonna do next
Doesn't
week,
work on the
but the
long
final presentation is what's really important. So I think you ought to try to plan,
Means if you want to make it into product, or you want to do
try to
something.
take what you're doing and relatively relatively small steps, so that's, you know, you're confident you can get.
It's hard to say because you're trying to provide user interface. You can't predict what user
But
does.
I haven't recently.
You'll show me next week, that's fine, you know, when I schedule it,
User
but
has energy.
I'm just saying.
No, the
you know,
user doesn't add energy to the system.
Right now, you know, that's where you are.
Simulation model. Because
That's what I mean.
no,
To get a
but
better
when user
grade,
interact with the
you'll
graph,
need to do
add energy. Yes,
relatively
but
speaking.
you already know that. You can track that. Even you position it in your model.
You know,
you can do that.
nothing wrong with what you did, it was just that it wasn't
the
as,
simulation
it
itself.
wasn't nearly as challenging as the original project. was. It wasn't as challenging as.
That's what I'm saying. I'm saying if it's
I understand.
Yeah, that's what
you really, you know, you need to
I'm
get a
trying to
job.
like,
That's really, really
trying to
important. to you.
adjust the-
I don't have an issue with you. I'm just trying to tell you.
So I don't have to adjust the
Exactly.
it's just
you kind of have to because
Well, why don't you think about it a little bit, and then let's have a conversation when you present next week. So, I will schedule you and Martha for sometime next week. And,
or something
probably
the
Tuesday.
restriction model will get harder, more complicated.
Or it's possible that it might.
For instance, we saw that when you're
In the morning at 11, if you guys can do it then, because Tuesday at 11, you know, I'm waiting for my email, so I gotta look at my
doesn't come
There's
to
this friction.
Should I send you a
what I'm trying to say is,
on Friday, send me just a Friday email.
I'm
Schedule
general
for the.
information.
The graph visualization, I would see how.
if you're trying to interact with it, if you're trying to provide user interaction, then you have to make sure the model is under your control. So,
How much, how are the users?
Probably have a problem about
you don't know how the information model uses energy.
So we were presenting on the fifth to the fifth and sixth.
Yeah, eventually,
taken out of
I know,
the
eventually,
depend on
you don't know how long.
to go to New York City.
It could be like taking 6 minutes.
Oh.
That's
you got
fine,
it, you
I
got it.
guess, but it really is a problem. If you want to fix
Could you
it,
present on
you
the
have
sixth?
to, have to make the friction
So you were scheduled to present on the fifth, but you're gonna be in New York
much
City.
more complicated.
Is that correct?
Which is
Could you
not-
present on the sixth? Will you be back by the
Yeah,
sixth?
I understand, it works, we like,
Actually,
I did this, it works. Friction works.
Maybe I can, they'll come here.
I'm not gonna change the
Maybe I can
friction.
just,
No, you should,
exam
because,
out and then come back to Circuit
makes
and
things-
present some.
you just introduce a different friction.
Do that?
It works. I've did this already, it works.
I'll try.
Better approach was.
Send me an email about it.
Yeah, I may do that, but I don't. What do you mean?
That would be, I know that would be hard on your parents, because they took a long flight in and then take a long drive back, it's bad. Send me an email about it, I'll think about it a little bit, maybe I'll just, So one option would be for you to present before you go. Would you be ready to present before you go? Send me an email about it, and I could, I can
It's a constant
move your
approach.
presentation to later. I don't really want to, because, I got a lot of grading that I gotta get in and stuff like that is the problem. So, but send me an email about it. We'll work something out. It would be, certainly would be hard on your parents to spend all that time flying in and then turn around immediately and take a long drive back to Syracuse, so. We'll do something.
You could do that.
I'll
Okay,
probably
yeah,
wind up
I-
scheduling.
can also-
If you think you can't present before the fifth,
I tried to.
then why don't you think about it a little bit and see if you think you could. If
So I
you
looked
can't,
up-
No,
then
you're
I'll
not
send
trying
you
to make it
later.
real. That doesn't make sense. We're trying to make it real.
But do send an email by, on Friday about it.
That doesn't mean.
I'm trying, yeah.
For instance, you can also add static friction, larger constant. And if
Something is
if the node is
The constant
no,
is
no,
like-
if the node is velocity is smaller.
something was it zero.
And I'm trying to say,
你 demo 的时候没有必要去
have
demo 的 P value 的信息。
you won't be able to.
就如果你是为了 demo
I mean the
blockchain 做
traction
到 information synchronization，那你就只需要做一个很简单的一个 text，
to add
输一个
traction
text 在3000这边，send 了之后，然后在4000这边 refresh。
That's
因为
velocity.
synchron，因为你的 blockchain 它可以
What I mean
synchronize， 直接
is
这边
like
就
this
看到了。
threshold.
这样 demo 你不用去解释你的这个
You
P
make the
value。
friction a little bit larger than normal.
You know, your physical model,
Flaw.
the equations model can be perfectly stable, and your discrete representation of it be unstable. All of the explicit integrations where you are taking an explicit step, you're only using information from where you are to take the next step. All of them have the issue that they will go unstable if that step size gets too big. All will, independent of whether your system is stable or not. But there are schemes that are called implicit integration schemes that iterate so that you're building, in each iteration builds information about the state of this next step. And you're iterating back and forth. So now it's a much more expensive computation.
Can that be done?
None of this is real time. None of this is real time. None of this is real time. Okay, I mean, depending on the parameters of your system, it might be oscillating, full cycle once every microsecond, But those kinds of calculations can be done if you use efficient distance measures, not Euclidean square root of the sum of the squares, which is expensive to calculate, but if you use measures like the largest coordinate, the magnitude of the largest coordinate, which is quick to calculate. But we're not asking you to do, I don't think you should do that. But that's.
One of my goals was to make it look real.
Yeah. No, none of us, I don't think you should change. I don't think you should change it. But I think some of the oscillation you were seeing may be an artifact of that discretization that you're doing to this.
All of the
Some should, some should,
I
but
think-
you don't know, you want to feel that all those wiggles are in response to your continuous equations, but they're not necessarily. That's all we're saying. The effect of this discretization might be very tiny, might not even be measurable, okay? But on the other hand, it might make it go unstable.
I think
I'm not asking you to worry about
I think the friction just.
No, you're wrong. You're absolutely wrong. I have done simulation. I did scientific programming for about 15 years. And I've explored it is a well-known, published, frequently published fact that all of the explicit integration schemes, the schemes that just use state from the past to take the next step, all of them go unstable if you make the step size big enough. All of them. All of them, independent of the amount of friction you have. The more friction you have, it may make the step size a little bigger. The Point is
So-
that
so what if-
anytime the step size is bigger than the smallest time constant in the system, it'll go unstable. But
What if my
you do,
small enough?
Hmm?
What if my step size is
if it's small enough, if it's small enough, then the smaller it gets, the more accurate a representation, the closer your discretization gets to the continuous equations, but the slower it takes. It can take a really, really long time to calculate. All of this comes to a head for systems, they call them ill-conditioned systems, that have eigenvalues way down here and eigenvalues way up here, and the eigenvalues way up here make very slow modes change, and the eigenvalues down here make very fast little ripples on them. And the point is, with the fixed integrations, you can't take a step size bigger than some constant of those tiniest little oscillation time constants. So if you have an ill-conditioned system which might have eigenvalues spread by 10,000, it says, I'm taking these tiny, tiny steps, desperately trying to, and it takes forever to see those slow modes. Well-known fact on physicists, mechanical engineers, electrical engineers, that's me. Okay, and if you've been working in that area, so I can send you some references. If you're interested. I'm not asking you to do anything. I don't think you should do anything.
at least I want to know about. So you mentioned something.
Gear's algorithm.
Gear's
Is a
algorithm.
guy who published one of the most widely used implicit integration schemes. It's a fairly efficient scheme for doing this implicit. So what you're doing, each step size you're iterating. To take each step, you iterate a number of times, and there's a bunch of schemes, but normally, normally that it's a lot faster to do that iteration and take fairly big steps than it is to take these little tiny steps with no iteration.
For each step, I'm just trying to.
You are, because you have an explicit integration. Implicit integration means I don't have all the information I need to make that step, and by that iteration, you're building up the information you need to make that step. That's why it's called implicit. And it's only when the system is really ill-conditioned, widely separated time constants that it matters. And what happens with these implicit integration schemes is you see them take little tiny steps when it's rippling fast, but as soon as those fast modes die out, it starts taking bigger and bigger clump steps. So you see the fine detail, but you also see the slow modes in a reasonable fashion. So your progress through this time trace is not linear. You're going really slow when it's doing these fast ripples, and then you make bigger, so up to some point.
I'm wondering, can all these iterations happen?
Depends on how big your system is. The answer is absolutely not if it gets big enough. But see, real time doesn't mean anything for you. You want to do it at a rate that people seeing your visualization see it moves, okay? And I think probably.
So that means like this computer.
No, doesn't mean that at all. Doesn't mean that at all. Because you can take your system and scale all its, change its parameters so that you've taken, the question is, where are the eigenvalues? Do you know what an eigenvalue is, a principal mode? Do you have enough physics to? Okay, kind of. Well, so you can take all those principal modes that are here, just move them all down, okay, so that the total time it takes is small. You're changing the scale factor on the time axis is all you're doing. Scaling those frequencies down. And so, yeah, you can still make it perfectly usable for the user, what you would see with that kind of a scheme, using this implicit integration, you wouldn't see those small little ripples anymore, because you'd be just jumping over them. You would be, but you're taking these big steps and doing the iteration, so you'd see the big. And, this isn't anything you're gonna do in this project, nothing that certainly don't expect you to. If I were in